All right, welcome to problem set 13. This one is a little more integral heavy, or antiderivatives as you'll probably hear them called in class. Just a reminder, antiderivatives are the opposite of derivatives, and they are the exact same things as integrals. It's just two different names for the same thing. So if I want to find all of the antiderivatives or all of the integrals of this function here, I just have to think about what rules I would have applied for doing a derivative with this and undo them pretty much. So if I want the integral of this right here, well, I know that when I take the derivative of a term like this, I subtract 1 from the exponent. So I'm going to add that back on. And I also normally put that exponent in front to multiply, and the opposite of multiplication is division. So I'm going to have my 6, and now it's divided by that right there. And that might seem confusing, but we can always double check that, right? If I now took the derivative of this term, I would have a 4 times my 6/4 times x to the power of 4 minus 1, which is just power of 3. These 4's cancel, and it turns into a 6x cubed. So that's looking right. So that first term, the integral is just that. Our second term, we do the exact same thing, so that x would have been an x cubed and not an x squared. So it's minus 2 divided by 3. And then plus, well, this is a 7, but we know that when we take the derivative of a constant, it disappears. So this couldn't have been a constant before, so it had to be multiplied by an x. So it's going to be plus a 7x. And another way to think about that, right, is this is now an x to the power of 1. If I have a 7 times x to the power of 1, and I take the derivative of that, that's just 1 times 7 times now x to the power of 0. And anything to the power of 0 is just 1, so it just turns into 7. So it looks like this is right as well. But we want to find all of the integrals for this, which means we have to add a plus c. What the c is right here, this stands for constant, and that just means that there could be a constant in this equation before the derivative was taken, and we have no way of knowing what that constant is without other details about the function. For example, this could be all of this, then plus 3. Right? When I take the derivative of that 3, it's going to completely disappear and I'll never see it again. But it could also be a plus 7. It could be a plus pi. We have no way of knowing. So we just add a plus c. And that's all we need to do to account for that. Some of the later questions will have us solving for that missing constant. So we'll get to try that soon. It looks like this next one has us doing that actually. So we want to determine the original function if the derivative of it is this right here. So I'm going to be honest, I just realized that I didn't actually go through and figure out what methods for taking antiderivatives she has gone over. But I'm going to do this the way that I know it best. So I'm going to take the integral of my negative 2/3 sine of x times cosine of x. And this is tricky because this is a product here. And when we take the derivative of a product, we have a special rule for that, right? We have a product rule. But when we end with a product, it's a little different. We have to use what we call u substitution. Obviously, you don't have to use a u. You could use any other variable for this, really. But it's common practice to use a u for the substitution. And I want to identify a u. Oh, and this is all with respect to the derivative of x, right? So I want to find a u that I can pull out of here and that the derivative of will also be able to pull out. So for this, I know the derivative of sine of x is cosine of x. So I'm going to say that u equals sine of x. And then du, right, or the derivative of u, would equal cosine of x times the derivative of x, right? Because it's with respect to x. So now if I plug in this, this is going to turn into the integral of negative 2/3 times u times du. And this du just replaces the dx. It tells us what we're taking the integral with respect to. And we can just plug in that du because it equals this, and we've got that right there. Now, it's just me taking the integral of essentially this. And since this is a constant coefficient, I can actually pull it out in front. And now I'm really just taking the derivative, or the integral of u. Well, u is a u to the power of 1. If I'm going backwards, I know that's gonna, if I add 1 to my exponent, it's gonna turn to a u squared. And in order for there to be nothing in front here once I take that derivative, because if I took this derivative, I would get 2u. So I know that has to be 1/2 u. So if I take that now, it's going to be 2 times 1/2 u, which is just going to equal u, which checks out, which means that our integral is going to be negative 2/3 times 1/2 u squared. Those cancel. Turns into a negative 1/3 u squared. And now we just plug back in u. And so the integral here is a negative 1/3 sine squared of x. And oh, I made a really common mistake, which is forgetting my plus c. You always want to write your plus c just so you don't forget it, because forgetting it can mess up your equations. But this is our function. So I know that f of x equals negative 1/3 sine squared of x plus c. Now we want to figure out what c is, right? Because that's an important aspect of our function. We want to figure out the exact original function that they took the derivative of to get this here. Well, they gave us the extra details that we need for that. They told us a point on the function. So if we want to find what c is, this is like solving for our like y-intercept in like a y equals mx plus b situation. Well, I know that f of pi over 2 equals 4. So when x is pi over 2, f of x is 4, which means that this turns into a 4 equals this. Okay, I know sine of pi over 2 is 1. 1 squared is 1, which means that 4 equals negative 1/3 times 1 plus c. 4 equals negative 1/3 plus c. Then I add 1/3 to both sides. C equals 4 1/3. And now I've got my a is a negative 1/3. My b, we know our original function is a sine squared, times cosine to the power of c. Well, we don't have a cosine in our function, which tells me that this cosine to the power of c has to be a 0, right? Because that would turn this term into a 1. And then plus d, where d is our constant. We just solved for that. So it's 4 1/3. Or I could write that as 13/3, or you might put that in decimal form for the actual homework. Totally up to you. The next one is a pretty similar one, except a little less complicated. This one, our derivative is negative cosine of x. Well, I know pretty well my trig derivative rules that the derivative of sine of x is cosine of x, which means that to get a negative cosine of x, I have to take the derivative of a negative sine of x, which means that the antiderivative of this, or the integral, is just going to be a negative sine of x plus any constant that was there before I took that derivative. Now, once again, we've got a point. So I know this equals 0 when I have this. Again, I know sine of pi over 2 is 1. So that means that 0 equals 1 plus c, which means that c equals negative 1. Now, we've got our a is a negative 1. B is a 1. Cosine to the power of c. There is no cosine, so again, our c is 0. And our constant, d, is a negative 1. Number 4 is just a little bit trickier, just because it's an e to the power of something. And I know that if I was to take the derivative of this, I would have to use chain rule a little bit. And this was just kind of difficult to think about. So I'm going to try my best to explain how I like to think about it. Doing this, I know that the derivative of e to the power of x is always just itself, right? I know that the derivative of e to the power of something times x, like 2x, is going to be chain rule. I'm going to multiply that in front. And it's always going to be like that. Therefore, if I take the derivative of this, that's just going to be 2/3 times e to that. Okay? You see where I'm going with this? Well, if I was to take the derivative of something to get this, I would just have to have this, but times something that's going to cancel out with this, right? So what times 2/3 cancels out? Well, that's going to be 3/2. So if I undo that, I'm going to say that's 3/2 e to the 2x over 3. And now if I take the derivative of that, I'm going to get, if I take the derivative, just to double check it, right? If I take the derivative, that's going to get 2/3 times my 3/2. Those cancel, and then it's all just times that, which is our answer. So I can safely say that our original function is this right here. It's going to be 3/2 e to the 2x divided by 3, and then plus any constants that existed before that derivative. Okay. Oops. All right. And now, for this next bit, they give us that when x equals 0, the function equals 3/2. Therefore, I have 3/2 when I have this, and then I've got 2 times a 0. It's just 0, so it's 0 over 3, which is just 0, so it's e to the power of 0, all plus c. 3/2 equals, well, anything to the power of 0 is 1, so it's just that. And then if I subtract that from both sides, I'm going to get, well, that's a 1.5, so it's just going to be 2 equals c. I can go ahead and change that in my original function. Boom. There's our function where a is 3/2, b is 2/3, and c is 2. Number 5 is a different type of problem. We're going to have to apply the mean value theorem for this one. And it's just a little interesting. So it says that a driver slowed to a halt in 30 seconds while skidding 2,100 feet. If the speed limit was 40 miles per hour, can we conclude that the driver was speeding? Well, I know that they go a distance of 2,100 feet over a time span of 30 seconds. So I know that t equals 30, our final time is going to equal 30, and our initial time, when they started the skidding, is 0 seconds, obviously, because it took them 30 seconds. So they start skidding, and then it takes them 30 seconds. And I know that whatever our function is, f at that initial point is going to be 0, because they haven't traveled any yet, because this is their starting point. I know that the function at this end time here is going to be this distance they traveled, because we're thinking about the function of the distance they traveled. Well, I can look at that with my mean value theorem, and I know that with the mean value theorem, I have f of b minus f of a over b minus a. In this case, b is our final time, a is our initial time. So I'm going to have 2,100 minus 0 over 30 minus 0 equals this, which then turns out to be 210 divided by 3 is just going to be 70 feet. So at some point when they were skidding, because this is the mean value in that time, at some point they were going at 70 feet per second. Well, I know that 60 miles per hour is, I think it's 88 feet per second. I think that's correct. The speed limit was 40 miles per hour. So that tells me that, well, I know 30 miles per hour would then be half of that. I've got myself a little stuck here. Did not consider that. So speed limit was 40 miles per hour. Well, I know that 45 miles per hour would be a solid 66 feet per second. No, that's incorrect. It would be 70 something. So that doesn't actually help me. Shoot. Am I dumb? Hold on. Yeah, so 45 miles per hour would be 66 feet per second. 70 feet per second, if it's greater than 45 miles per hour, then it's greater than 40 miles per hour, which means that the mean value they were going is greater than the speed limit, which means that we can conclude they were speeding. At some point in there, they had to have been speeding. And obviously, since they're slowing to a halt, they must have been speeding before they began skidding, if they were speeding at some point during the skid. Yeah. Let's try the next one. We want to find our extreme values, which this is something that we've done on the other homework. So let's give this a go. It says if we have a function g of x equals sine of this in here. Oops. Okay. On the given interval, I want to find all extreme values of g on that interval. Okay, well, first of all, I have to take the derivative of g of x, which means we'll have to use our chain rule. So it's going to be this. I know derivative of my inside is pi over 2 times the derivative of my outside is cosine. So it's all this. Okay. And now I set that equal to 0 and find my critical points and then check if any of them are on the given interval. So if I set this equal to 0, this will be 0 whenever cosine of this equals 0. Which means I know that cosine of x equals 0 when x equals pi over 2 or 3 pi over 2. So if this is the inside is a pi over 2, I know that, oops, I don't want to use an x for that actually, sorry. Let me use a different variable so it's not confusing. So I know that my x has to be either a 1, a 3, or like a repeat of that, right? It could go all the way up to there, which means my critical point, only one that's even close to my interval is 1, okay? But it's not actually included in my interval, right? Because this is non-inclusive. So we're just going to evaluate if the function is increasing or decreasing on the given interval, okay? Because that is what that is. So on this interval, let me just plug in a point in here. I'm going to plug in maybe a 1/2. So if x equals 1/2, then I get pi over 2 times cosine of pi over 4, right? Because pi over 2 times 1/2 is going to be pi over 4. And that's going to be pi over 2 times the square root of 2 over 2, just based on our unit circle. This is positive, which means it's increasing on this interval, which means that our maximum we can't determine because we don't have any critical points on the interval. So we're just going to put that it does not exist, right? Because our maximum would theoretically be at that 1. But since that 1 is outside the interval, there is no maximum on this interval that we can determine. Our minimum, however, is just going to be at 0. Because it starts at 0, it includes 0 all the way down here, and it's increasing on this interval all the way up to when x equals 1, but it doesn't actually include that. So 0 is our minimum. What is the value of our function when x equals 0? Well, sine of this is going to be 0 because it's the same as sine of 0. So boom. Let's take a look at the next one. It's a pretty similar one, but it's a little more confusing because there is that natural log. So we want to find, again, all the extreme values on this given interval. So we're first going to take the derivative. In this case, I need to use my chain rule. So I know my outside is a natural log of something, right? And my inside is this quotient. I know that my derivative will be this, just because of how I take the derivative of natural log. And now the derivative of this is going to be a little bit of quotient rule, right? So our low d high minus high d low over low low. That's going to be x squared plus 16 times the derivative of x, which is just 1, minus x times the derivative of the low term, which is just 2x, all over x squared plus 16 squared. And I'm going to keep it in those terms, which this tells us that my derivative is, let's see, it's going to be, I'm actually going to combine like terms before I fully write that out. So it's going to be x squared plus 16 minus, distribute that, that's minus 2x squared, which is just negative x squared plus 16 over x squared plus 16 squared. So then if I plug that in up here, it's going to be this, which is that derivative we just found, times 1 over v, which is, if it's 1 over a quotient, it's going to flip that on its head. So it's going to be x squared plus 16 over x, in which case I see an x squared plus 16 cancels, but this is squared, so there's still an x squared plus 16 down there. So it's now this, putting the x in front, times that remaining x squared plus 16, and that's what we've got now. So I'm going to go ahead and write that. So that's our derivative, okay? There's a good little bit happening there, so feel free to pause, rewind, what have you. But that should be our derivative. That should be correct. Now I need to set that equal to 0. Well, I know that it will only ever equal to 0 when my numerator equals 0 and my denominator is incapable of equaling 0, right? Because this bit will always be positive, and this, which means that this can never equal 0. So the only reason my denominator would equal 0 if it's x equals 0, but that's not even on our interval, so we're not going to try that. So I know that this derivative equals 0 when the numerator equals 0. So I'm just going to do this. So now it's negative x squared equals negative 16, because I subtracted 16 from both sides. Well, they're both negative, so I can just cancel that, right? X squared equals 16. X equals plus or minus the square root of 16, which means that x equals plus or minus 4. It could be negative 4, it could be positive 4. Looking at our interval, though, only positive 4 is on the interval. Therefore, x only equals 4 on this interval. That's our only critical point that we're going to consider. So now we're going to take a look at our interval. So it's 1/2 up to 4, and then it's 4 up to 16. And I want to know which intervals it's increasing or decreasing on. So let's just plug in a value. I know 2 is between 1/2 and 4, so that'll be on this interval. Let's go ahead and plug that into my derivative, see if it's increasing or decreasing. Well, that's going to be a -4 plus 16 over 2 times 4 plus 16. So my numerator is going to be positive, my denominator is going to be positive. Therefore, on this interval, it's positive, and therefore increasing. Let's try a value for the next one. Let's use a nice easy one. I'll use 10. That's on this interval here. So h prime of 10, that's going to be -100 plus 16 over 10 times 100 plus 16. I know -100 plus 16 is going to be negative, so my numerator is negative, but denominator is positive, which means that overall it's going to be negative, and therefore decreasing on this interval. Which means, and we can go ahead and draw this out. So when x equals 1/2, all the way up to when x equals 4, it is increasing. Okay, that's what we determined. All the way up there, it's increasing. And then from 4 all the way over to x equals 16, it's decreasing. Which tells us that our minimum could be at either of these 2 points, so we'll have to evaluate those, but our maximum on this interval has to be when x equals 4. So h of 4 is our maximum. Let's go ahead and evaluate that. So h of 4 is going to be a natural log of 4 over 16 plus 16, right? Which is just natural log of 4 over 32. Again, natural log of 1 over 8. So, and that's how I'm going to input that. You could put that in your calculator and put that in if you like, but that's how I'm going to write it here. Just natural log of 1/8. Now we need to figure out what our minimum is. And again, we see with our drawing, a little sketch, that our minimum could be at x equals 1/2, but also could be at x equals 16. So I need to now compare them to see which h value is actually smaller than the other. So I'm going to have to plug in h of 1/2 as well as h of 16 and see what I get. Let's start with the h of 1/2. It's going to be natural log of 1/2 over 1/4 plus 16, which is natural log of 1 over 2 times 16 and 1/4, or natural log of 1 over 32.5. Okay. Which is a little confusing to read, but I'm just going to leave it like that for now. Let's try the h of 16. It's going to be natural log 16 over whatever unholy number 16 squared is. Oh, it's not actually that big. That's 256, isn't it? Plus 16, which gets 256 plus 16, 272, I think. So natural log of 16 divided by 272. And I am going to reduce that a little bit. So it's going to be 8 over 136, 4 over 50, 65, 68, I think. Yep. Which is the natural log of 2 over 34, or 1/17. Well, I know that the bigger the number in my natural log, the bigger the actual answer is going to be. So whichever of these is smaller is going to be my minimum. And since this is dividing by a larger number, That one's going to be smaller, therefore minimum is at the 1/2, comma, this. And I am going to double check that just really quick with my calculator. So I'm going to go ahead and plug that in just to make sure that I did that correctly so that I don't mislead you guys. And yeah, this answer is going to be about negative 3.48124. And this answer over here is going to be about negative 2.83321, etc. Obviously, this answer is further in the negatives and therefore smaller. Okay. Now that we've knocked that out, I'm going to erase some of this so we've got room to do our limit for this next question. Number 8 asks us to evaluate the right-hand limit of this function here. Well, I'm going to start off by simplifying where I can. Why won't my undo button do anything? Hello? There it goes. Okay. So I'm going to start off simplifying where I can. So I'm going to get ahead and factor this out, actually. So I know my limit as x approaches 8 from the right side of this here is the same as all of this over, and if I factor this out, I see that this is a perfect difference of squares. So it's going to be 8 minus x times 8 plus x. Okay, and it looks like I should cancel these out, but I can't, because x minus 8 and 8 minus x are different. What I have to do instead is I have to factor out a negative from the bottom, and we'll see that in just a second. If I go ahead and factor out a negative from my bottom, it's going to be negative, and now I'm going to apply it to, yeah, this right here. So if I take the negative out of that, that turns into a negative 8 and a positive x, so it's negative 8 plus x, or I could rewrite that as x minus 8. Now times an 8 plus x. Factoring out that negative was important. Now I can cancel this. Now I get all this over negative 8 plus x, and let me see if I plug that in. Well, hold on. I know if I plug that in, that's obviously going to be, it's going to be like 8 over negative 16, so it'd be negative 1/2. But just to make sure that that is our limit, I do want to make one of our little tables of our x and y values. So this is from the right side, so I'm going to 8, 9, 10, 11, 12. And I'm just going to plug in all of those just to see how close they get us. So when x equals 8, that gets to be a negative 1/2. When x equals 9, that's going to be 9 over negative 17. When x equals 10, that's 10 over negative 18, which is negative 5/9. 11. Yeah. And this feels like it checks out, because it feels like going this way I'm getting bigger and bigger, and getting this way I'm getting closer to my negative 1/2. Or not bigger and bigger, but further in one direction. Let's just try a 12. That's going to get me yeah. So I think it's safe to say that this limit approaches negative 1/2 from the right side. In this case, probably from the left side as well, actually. But yeah, so now we want to determine f of x given this data. This is just like the problems we were doing earlier, so it should be nice and easy. We just have to take the integral or antiderivative of this. I know that would be an x to the 4th, and I know I'm going to divide by 4, so that turns into that. So, and obviously plus c. I know f of 1 equals negative 1/2. So I know negative 1/2 equals 1 to the 4th over 2, right? Because this times that, plus c. So negative 1/2 equals 1/2 plus c. If I move that over, I get negative 1 equals c. Therefore, f of x equals 1/2 x fourth plus negative 1, or just minus 1. All right, I think we've just got 2 questions left to go. Yep, number 10 and number 11 here. This first one gives us this function and asks us on what intervals is that function increasing and on what intervals is it decreasing. This is just like finding our extreme values, except we only care about the interval now, right? So I'm going to take my derivative, which is going to be 3x squared plus 3. I'm going to set that equal to 0 to find my critical points. So I get 3x squared equals negative 3. X squared equals negative 1. That doesn't seem right. I feel as though I made a mistake, because that doesn't exist. So I'm going to change that, actually. I'm going to change that to a negative number, just to avoid that, so that's not a problem for us. No, that was wrong. I'm going to leave it as it was. So equals negative 1. Because this means that there are no solutions, which means that it is not increasing or decreasing on any particular points. There are no critical points, which means we just have to evaluate from negative infinity to positive infinity, because that's the only interval that exists. There are no additional intervals because there are no critical points. So if I plug in a number at any point in here, it should tell me whether or not we are increasing or decreasing. If I plug in, let's say 0, f prime of 0 equals 3, right? Which is positive, so it's increasing always. It's increasing on the entirety of its domain. So increasing from negative infinity to infinity, and decreasing never. Slash dne. At no point is this function decreasing. For the next one, that feels kind of crazy to think about. For this next one, we are given this function here, and same question. On what intervals is it increasing? What intervals is it decreasing? I'm going to go ahead and rewrite this as this, just to make the derivative a little easier. We're going to use chain rule here. So let me go ahead and get that settled. Our inside is this. Derivative of our inside is that, which gets us, so it's going to be 72 over 2 times, okay, which is then 36 over 6x minus 6. All right, so our derivative, as I just found, is 36 over the square root of 36x squared minus 6. And we might actually rationalize that. I could also write that as this here is that. Okay? So now I want to set that equal to 0 to figure out where our critical points are. So we're going to use the rationalized version because it's makes more sense for us to use. So when does this equal 0? Well, this is going to equal 0 whenever our numerator equals 0, right? So, and that'll only happen when the inside of this radical equals 0. So when is that? When does 36x squared minus 6 equal 0? Well, 36x squared equals 6. X squared equals 1/6. Therefore, x equals plus or minus the square root of 1/6. Yeah, that should work. So let's see. Are there any values for which this is undefined? Surely there are. So that would just be whenever this is less than 6, which would be, I suppose, whenever our x squared is smaller than the square root of 1/6, which, so that would be plus or minus, I believe, or the square root of 6 is another way I could write that. I think that's right. Feel free to call me out if this is wrong. So I think that would be just when x is less than the negative, well, no, greater than, oof, oh, that's hard to wrap my head around. Okay, so it has to be less than this, but greater than, oops, I always erase the wrong things, this, I think. Yeah. No. Yes. Hold on. Yeah, because if it's greater than this, then that won't ever be smaller. Sorry, I'm really tired. It's Tuesday. I haven't had a long week. It feels long. Okay, which means that our intervals are going to be negative infinity up to this point. And then, of course, we have here, on which we know it is undefined. And then we have our final interval, which is from here all the way up to positive infinity. Now that we've got that situated, sorry if that was confusing. It's really difficult for me to wrap my head around that. Now I want to evaluate on which of these intervals it is increasing or decreasing. So again, I'm just going to pick a number in this interval here and plug it in up there. Let's pick a nice easy number to work with. I'll pick -2. So h prime of -2 is going to be, and I'm going to use the non-rationalized version because I think that's easier for me to work with. It's going to be square root of that, and that'll be positive. It is therefore increasing on that interval. And then let's pick another value. I'll just pick a +2, and it should be increasing on that interval as well. Right, because that shouldn't actually change anything because of the x squared. And I'll just plug that in to show you. Get 36 over square root of 36 is still going to be times 4 because 2 squared is 4 minus 6, so it's all positive. Therefore, it is increasing from here and here, decreasing also never, just like the other one, so D and E, and is undefined along this interval. And that is it. That is all that this homework is. This was a little bit of a shorter one, I feel like, though I might have taken about the same amount of time on it. We're getting into territory that's a little bit more difficult for me to explain. So I hope that these videos are still helpful. But yeah, Thank you for watching. I hope this was useful.